Engineering vibration analysis for rotating machinery, techniques to monitor and diagnose machine vibrations. Vibration analysis overview, fundamentals of mechanical vibration, Rathbone chart, historical perspective, ISO 2372 and ISO 10816 standards, vibration measurement units, machine condition categories, importance of frequency analysis, effect of machine size and power, practical vibration measurement, engineering judgment in vibration analysis, conclusion and key takeaways. Vibration analysis is a core condition monitoring technique used in engineering maintenance to evaluate the mechanical health of rotating and reciprocating machinery. It is based on the principle that most mechanical faults, such as imbalance, misalignment, looseness, bearing defects, and gear wear, generate distinct vibration patterns. By measuring and interpreting these vibration signatures, engineers can detect developing faults long before they result in catastrophic failure. This proactive approach supports predictive maintenance strategies, reduces unplanned downtime, improves safety, and extends equipment life. In industrial environments, vibration data is typically collected from critical assets such as pumps, motors, compressors, turbines, fans, and gearboxes. Sensors such as accelerometers or velocity transducers are mounted on bearing housings or machine structures to capture vibration signals during operation. These signals are then analyzed in both time and frequency domains to identify abnormal behavior. Overall vibration levels provide a quick assessment of machine condition, while spectral analysis helps pinpoint specific fault sources. Engineering standards play a crucial role in vibration analysis by providing objective criteria for evaluating machine condition. Historical references like the Rathbone chart offered early guidance on machine smoothness, while modern standards such as ISO 2372 and ISO 10816 establish globally accepted vibration severity limits based on machine size, power, and operating speed. These standards enable engineers to classify vibration levels as good, allowable, tolerable, or not permissible. This presentation introduces vibration analysis from an engineering perspective, focusing on vibration severity evaluation using the Rathbone chart and ISO standards. Emphasis is placed on understanding vibration units, frequency considerations, machine size effects, and practical measurement techniques. The goal is to equip engineers with the technical foundation and professional judgment required to apply vibration standards effectively in real-world industrial applications. Mechanical vibration refers to the oscillatory motion of a machine or component about its equilibrium position. In rotating machinery, vibration is primarily caused by dynamic forces generated during operation. Understanding the fundamental vibration parameters, displacement, velocity, and acceleration, is essential for correct interpretation of vibration data. Each parameter provides different insights depending on machine speed and fault type. Vibration displacement measures the physical movement of a component and is commonly expressed in mils or micrometers, peak to peak. It is most useful for low-frequency vibration, such as that caused by imbalance or misalignment in slow-speed machinery. Vibration velocity, typically measured in inches per second, in/SEC, or millimeters per second, mm/SEC RMS, is widely used for general machine condition assessment because it correlates well with mechanical stress and fatigue over a broad frequency range. Vibration acceleration, measured in Gs or meters per second squared, is particularly sensitive to high-frequency events such as bearing defects and gear mesh issues. Accelerometers are the most commonly used sensors because acceleration data can be mathematically integrated to obtain velocity and displacement. Another critical concept is vibration frequency, which represents how often vibration cycles occur per unit time. Frequency is usually expressed in Hz/Hz or cycles per minute, CPM. Different mechanical faults excite vibration at characteristic frequencies related to rotational speed, bearing geometry, or gear tooth count. Therefore, understanding both amplitude and frequency is fundamental to accurate diagnosis. Engineering vibration analysis relies on combining these parameters with machine knowledge and operating conditions. No single vibration metric is sufficient on its own. Instead, engineers must evaluate vibration behavior holistically to make reliable maintenance decisions. The Rathbone chart, introduced in 1939 by T. C. Rathbone, represents one of the earliest formal attempts to classify machine vibration severity. It correlates overall vibration velocity, measured in inches per second peak, with qualitative descriptions of machine running conditions such as very smooth, smooth, slightly rough, rough, and very rough. At the time, this chart provided valuable guidance for maintenance engineers who lacked standardized vibration assessment tools. The chart is based on filtered vibration velocity measurements taken on machine structures or bearing caps. It establishes threshold values, for example identifying approximately 0.039 in/SEC peak as good, 0.0785 in/SEC peak as fair, and higher values as increasingly rough. These categories offered a practical way to assess machine condition using simple instrumentation. However, from a modern engineering standpoint, the Rathbone chart has significant limitations. It does not account for vibration frequency content, machine size, operating speed, or specific machine design. As a result, it can misrepresent the severity of vibration in certain applications. For example, high-frequency vibration at low amplitude may be more damaging than low-frequency vibration at higher amplitude, yet the chart treats them equivalently. Despite being considered obsolete for detailed diagnostics, the Rathbone chart remains useful as an educational reference. It illustrates the historical development of vibration standards and helps engineers understand why modern standards evolved. It also provides intuitive insight into the relationship between vibration velocity and perceived machine smoothness. In practice, the Rathbone chart should only be used as a general guide and never as the sole basis for engineering decisions. ISO 2372 and its successor ISO 10816 are internationally recognized standards that provide vibration severity guidelines for evaluating the condition of industrial machinery. These standards were developed to address the shortcomings of earlier approaches by incorporating machine size, power rating, and operating speed into vibration acceptance criteria. ISO 10816 classifies machinery into different groups based on power output, such as machines below 15 kilowatts, between 15 and 75 kilowatts, and above 75 kilowatts. For each category, vibration velocity RMS limits are defined and grouped into condition zones, typically ranging from Zone A, good, to Zone D, not permissible. This structured approach allows engineers to assess vibration severity in a consistent and repeatable manner. One key advantage of ISO standards is the use of RMS velocity in mm/SEC, which better represents the energy content of vibration and its potential to cause damage. For example, a medium-sized machine may be classified as good if vibration levels are below approximately 1.12 mm per second RMS, while higher levels may be considered tolerable or unacceptable depending on duration and operating context. ISO standards are widely used in industry for acceptance testing, condition monitoring programs, and maintenance decision-making. However, they are not diagnostic tools. They indicate severity but do not identify fault type. Therefore, ISO limits should be applied alongside spectral analysis, trend monitoring, and engineering judgment to achieve reliable results. Accurate interpretation of vibration data requires a clear understanding of measurement units and how they relate to one another. Vibration displacement is commonly expressed in mils, thousandths of an inch, peak to peak, while velocity is expressed in inches per second peak or millimeters per second RMS. Acceleration is measured in Gs. Velocity is the most commonly used unit for overall vibration severity because it provides a balanced representation across a wide frequency range. Displacement is more sensitive to low-frequency vibration and is often used for slow-speed machinery such as large fans or reciprocating compressors. Acceleration is preferred for detecting high-frequency faults such as rolling element bearing defects. Conversion between units is frequency-dependent. For example, a given acceleration level will result in different velocity or displacement values depending on vibration frequency. This highlights why overall vibration numbers must always be interpreted with frequency information in mind. Engineering standards such as ISO 10816 specify vibration limits in velocity RMS, reinforcing the importance of consistent unit usage. Engineers must ensure that instrumentation settings, filters, and measurement bandwidths align with the selected standard to avoid incorrect conclusions. Machine condition categories are used to translate numerical vibration values into practical maintenance decisions. Terms such as very smooth, smooth, good, allowable, tolerable, rough, and very rough are commonly used to describe vibration severity. These qualitative descriptors help engineers communicate machine health to non-specialists and management. Under ISO standards, condition zones are clearly defined. Zone A typically represents new or overhauled machines operating within expected vibration limits. Zone B corresponds to acceptable vibration for continuous operation. Zone C indicates unsatisfactory vibration where corrective action should be planned, while Zone D represents vibration levels that are not permissible and may lead to immediate damage. It is important to recognize that these categories are guidelines rather than absolute rules. A machine operating in Zone C may continue to run safely for a period depending on load, criticality, and redundancy. Conversely, a sudden change in vibration within acceptable limits may still indicate a developing fault. Effective vibration analysis therefore combines condition categories with trend analysis and fault diagnostics. This integrated approach ensures that maintenance actions are timely, cost-effective, and technically justified. Frequency analysis is a cornerstone of professional vibration diagnostics. While overall vibration levels indicate severity, frequency spectra reveal the source of vibration. Each mechanical fault produces vibration at characteristic frequencies related to rotational speed or component geometry. For example, unbalance typically appears at running speed, 1 times RPM, misalignment often generates vibration at 2 times RPM, and rolling element bearing defects produce high-frequency vibration at calculated bearing fault frequencies. Gear defects generate vibration at gear mesh frequency and its harmonics. Without frequency analysis, vibration assessment is limited to severity evaluation and cannot support accurate fault identification. This may lead to unnecessary maintenance or missed failure modes. Modern vibration analyzers use fast Fourier transform (FFT) techniques to convert time-domain signals into frequency spectra, enabling detailed analysis. Engineering best practice requires correlating frequency data with machine design, operating conditions, and historical trends. This disciplined approach distinguishes professional vibration analysis from simple vibration monitoring. Machine size and power have a significant influence on acceptable vibration levels. Larger machines generally tolerate higher absolute vibration levels due to greater mass and structural stiffness, while smaller machines are more sensitive to vibration. This is why ISO standards classify machines by power rating. For example, a vibration level considered acceptable for a 100 kW motor may be unacceptable for a 5 kW motor operating at the same speed. Applying a single vibration limit across all machines can therefore result in incorrect assessments. Engineers must also consider machine foundation, mounting, and operating speed. A rigidly mounted machine will exhibit different vibration behavior compared to a flexible or skid-mounted machine. Understanding these factors ensures that vibration standards are applied correctly and consistently. Professional vibration analysis always accounts for machine context rather than relying solely on numerical thresholds. Accurate vibration measurement is essential for reliable analysis. Sensors must be mounted securely at appropriate locations, typically on bearing housings in radial and axial directions. Poor mounting can significantly distort vibration readings. Measurement parameters such as frequency range, filters, and averaging must align with the analysis objective and applicable standards. Consistency in measurement technique is critical for trend analysis, as variations in setup can mask or exaggerate changes in machine condition. Environmental factors such as temperature, load variation, and process conditions should also be documented. These factors can influence vibration behavior and must be considered when interpreting results. A disciplined measurement process ensures that vibration data is repeatable, comparable, and suitable for engineering decision-making. Vibration standards and charts provide valuable guidance, but they cannot replace engineering judgment. Every machine operates within a unique mechanical and operational context that influences vibration behavior. experienced engineers evaluate vibration data in combination with machine history, maintenance records, operating conditions, and other condition monitoring techniques such as thermography or oil analysis. This integrated approach reduces false alarms and improves fault detection accuracy. Engineering judgment is particularly important when vibration levels fall near standard limits or when trends change gradually. In such cases, decisions should be based on risk, criticality, and operational impact rather than rigid adherence to numerical thresholds. Ultimately, professional vibration analysis balances standards, data, and experience to support safe and reliable machinery operation. Vibration analysis is an essential engineering tool for assessing machine condition and supporting predictive maintenance. Historical references such as the Rathbone chart provide foundational understanding, while modern standards like ISO 10816 deliver structured and globally accepted severity criteria. Understanding vibration fundamentals, measurement units, frequency behavior, and machine context is critical for accurate interpretation. Overall vibration levels indicate severity, but frequency analysis enables fault diagnosis and informed maintenance planning. Effective vibration analysis relies on accurate measurement, consistent methodology, and professional judgment. When applied correctly, it reduces downtime, lowers maintenance costs, and enhances equipment reliability and safety. Engineers who combine standards-based evaluation with practical experience are best equipped to deliver reliable and defensible vibration analysis results in industrial environments.